In this short video, we will go through the type of reaction known as a redox reaction and how it's kind of different from some of the other reactions we've looked at thus far, and how to do one of the more important things with regard to redox reactions, and that is assigning oxidation numbers. So let's kind of look in big broad strokes first. What is a redox reaction? So a redox reaction, more formally known as an oxidation-reduction reaction, is a reaction where electrons are transferred from one reactant to another. Now there are a lot of different forms of redox reactions. It kind of falls into its own category, and it's kind of a broad category. We see in redox reactions some of the other signs of other kinds of reactions, things like single replacement or combustion or decomposition or synthesis reactions, where we have these electrons that are moving around as the molecules are rearranging. But in any of the processes, what we'll find is that when redox occurs, there are two processes that are happening at the same time. There's oxidation. Oxidation is the process where something loses electrons, and reduction is the process where something gains electrons. Now, these two processes happen simultaneously. The thing that is oxidized gives its electrons to the thing that is reduced. That is the flow of electrons as far as this is concerned. Now, it is very common and very easy for students to get the two terms confused and to identify things as oxidation when they're actually reduction and vice versa. Now, the easiest way around this are through mnemonics, just kind of little clever tricks to try to help us remember which direction is which. So there are two common mnemonics that are used. The first one, this is the one I actually learned with, is called Leoger. Leoger, L-E-O-G-E-R. Leo, loss of electrons, is oxidation. That's Leo. Gain of electrons is reduction. That's Ger. Leo the lion goes Ger. So it's kind of silly, but it's an easy way to remember it. And to remember what's actually happening in each of the processes. Now, another common way of going about this and remembering it is something called oil rig. Oil rig was not something I actually had heard until I was in college, but it is just as effective. And it's a little bit more tangible. It's something that's real as opposed to something that's silly. But what it stands for, oil, is oxidation is loss of electrons. Oxidation is loss, oil. Reduction is gain, rig. So oxidation is loss of electrons, reduction is gain of electrons. Now, what makes a oxidation-reduction reaction, a redox reaction, unique is that we can actually track the electrons as they're moving around. And the way that we can do that is through the use of something called an oxidation number. An oxidation number is a number that is assigned to an individual element in a given compound, molecule, ion, element, whatever. Is an individual number that is assigned to a given element in a substance that identifies its electronic environment at that particular moment in time. Positive, negative, or in the middle. Now, when it comes to assigning oxidation numbers, there are some tips and tricks that we can follow that will make things easier. One of the tips is that we have to recognize that the sum of all of the oxidation numbers in a substance has to equal the total charge of that substance. So what that means in particular is knowing that the sum of the oxidation numbers has to equal the charge. If I have an atom that is by itself in its pure elemental form, it's not going to have an oxidation number of anything other than 0. And 0 is a valid oxidation state. 0 means that there is no charge on that element at that particular time. Now, what we can also say is that if I have monatomic ions, like the chloride ion, like the oxide ion, like the sulfide ion, those elements are going to have, those ions are going to have oxidation numbers that are equal to their charge. So for a chloride ion, Cl minus 1, its oxidation number is minus 1. For barium plus 2, its oxidation state is positive 2. So that helps. That makes things a little bit easier. The other thing that we can look at is there are certain elements that have tendencies to have the same oxidation number all the time. And most of the time it has to do with electronegativity. Um, but the guidelines are these, and they're pretty simple. Fluorine. Fluorine is the most electronegative element on the periodic table. Its oxidation state is always going to be -1. The only time that its oxidation state isn't -1 is when it's an element. And that's because as an element, its oxidation state will be 0 because elements do not have charge. For hydrogen, when hydrogen is combined with metals and makes metallic hydrides, it'll have an oxidation state of -1. When hydrogen is bonded to nonmetals, it'll have an oxidation state of +1. When hydrogen is by itself, like all elements that are by themselves, they'll have an oxidation state of 0. And then finally, oxygen is going to have an oxidation number of -2. And that's going to be true for most compounds that oxygen is in. The only exceptions are if we have a peroxide. Peroxide has a -2 charge spread over 2 oxygen atoms, so each one has a -1 charge. And then elemental oxygen, like all elemental substances, has an oxidation state of 0. Everything else, if I use these two rules, comes down to a matter of algebra, where I can literally just set up an algebraic problem to solve for the missing charge, the missing oxidation state. And I'll show you in a couple of examples here. So sulfur dioxide, SO2, I can set up a problem where I know algebraically the oxidation state of sulfur plus the oxidation state of 2 oxygen atoms is going to equal to the total charge of 0, since sulfur dioxide is not a charged molecule. So if I approach it from that standpoint, I know that sulfur, I don't know what it is yet, but I know that each oxygen, since oxygen is not by itself and it's not a peroxide, is going to be -2, and there are 2 of them. So sulfur minus 4 equals 0. And if I follow the logic all the way through, sulfur is going to be +4. And so I can assign the oxidation state of sulfur as +4 and the oxidation state of the oxygen as -2. So that's really all that you have to do for these oxidation states. Set up an algebra problem where the total sum of all of the atoms is equal to the total charge, and then solve for what you don't know. Let's take a look at another example. I've got chromium plus 4 oxygens is equal to a total charge of -2. 2 minus charge on the chromate ion. If I use the same logic, chromium plus 4 times -2 gives -2. Chromium minus 8, because 4 times 2 is 8, is equal to -2. Chromium must be +6. And so the oxidation state of the chromium is +6. The oxidation state of the oxygen is -2. And we've assigned that one as well. And so I just can kind of follow this logic all the way through. I'll do another example. Nitrogen plus 3 hydrogens is equal to 0 charge. Nitrogen plus 3 times positive 1. Since hydrogen is reacting with a nonmetal, it'll have a positive 1 charge. Nitrogen plus 3 is equal to 0, and so nitrogen must be negative 3. So the oxidation state on the nitrogen is negative 3. The oxidation state for each hydrogen is positive 1. Let's do one more example, and then I'll pause for a second and let you try the last two. So for the chlorate ion, ClO3-, chlorine plus 3 oxygens is equal to negative 1. Chlorine plus 3 times negative 2 is equal to negative 1. Chlorine minus 6 is equal to negative 1. Chlorine must be positive 5. So I've got a positive 5 state on the chlorine. I've got a negative 2 state on each of the oxygens. Okay, so take a couple of seconds here, pause the video, and try to figure out the last two example problems here, the sulfur hexafluoride and the chlorine molecule. And then I'll come back in a couple of seconds and we'll see how you did. Okay, so for sulfur hexafluoride, we've got to use the same kind of logic. Sulfur plus 6 fluorines is equal to 0. Sulfur plus 6 times negative 1 is equal to 0. Again, remember, fluorine is going to carry a negative 1 charge almost always. Sulfur minus 6 is equal to 0. So sulfur must be positive 6. Positive 6 for sulfur, negative 1 for each fluorine, and that one's set. For the last one, chlorine, now we could approach this one logically. Chlorine is an element. As an element, we know that its oxidation state is 0. But if I had forgotten that, the algebraic method still works here as well. 2 times chlorine is equal to the total charge, which is 0. Well, if I follow my algebra through and divide each side by 2, chlorine would be equal to 0 because 0 divided by 2 is still 0. So this is the process that you have to undergo to assign oxidation numbers. And once you get good at assigning oxidation numbers, what we'll do next, and this will be the subject of the next video, will be to actually use these oxidation numbers to help us to balance redox reactions, which are a little bit more complicated. It's kind of like a blend of oxidation numbers and net ionic equations to figure out how to balance redox reactions. So until that time, have a good afternoon.